Good afternoon. My name is Daniil Sherki. I am AI researcher at Sber and PhD student at Skolkovo Institute of Science and Technology. Today, I will present a talk combining flow matching and transformers for efficient solution of Bayesian inverse problems. And we will first review the formulation of inverse problems, then cover the basics of flow matching and why it works. After that, I will explain why the transformer architecture is particularly suitable here and how it can be applied to Bayesian inverse problems. And let us begin with the problem formulation. Many real-world processes are described by mathematical models. Shown here is the forward problem of the diffusion equation in petroleum engineering. Given the permeability field and boundary conditions, we can compute the pressure field by using a PDE. In practice, however, we often observe only partial of a forward model. For example, five pressure points at the location. We may also know the boundary conditions, E in this notation, the experimental parameters that we can control. Thus, we have an observation function Z that depends on the experimental parameters E and mathematical model parameters M. But real-world observations are always noisy. Because the inverse problems is typically ill-posed, its solution is non-unique. Instead of single answer, we want the entire set of model parameters M that are consistent with given D and E. This calls for learning conditional distributions P with conditions on D and E, which can be done with generative modeling. Now let us discuss flow matching. Generative modeling aims to transform a simple analytical tractable based distribution into target distribution derived from real data, and flow matching is one such approach. By definition, it does not require complicated integration during training of continuous normalizing flow models. It's so powerful that the latest version of stable diffusion are no longer diffusion models but flow matching models. And there are several families of generative models. Direct maps, GANs, are hard to train but offer efficient one-step sampling. They do not learn the distribution explicitly, they learn approximately distribution. But continuous time microprocessors include diffusions models and flow matching. Flow matching is either to train and learns the exact likelihood directly. The figures show trajectories from the base to the target distributions. Diffusion models follow stochastic paths. There are where flow matching produce smooth deterministic trajectories, and next training a flow matching model and sampling from the learned distribution. Sampling proceeds by solving an orderly differential equations ODE with standard solvers like midpoint at very time step t in 0 to 1. The model predicts the velocity is the direction in which to move so that the current point reaches t equal 1. Now, about training, for each data point, we linearly interpolate between noise sample and real data. So xt equals this interpolation in time, and the loss function is this equation where x1 minus x0 is a true velocity and u theta is a model prediction. To make generation conditional, we supply u theta with information about the subs distribution we want to reach. The loss function is modified according to this equation. The resulting velocity field over time is illustrated here. But why does this work at all? A stochastic process satisfies the Kolmogorov forward Fokker-Planck equation, which governs the time evolution of probability density. Removing the stochastic term yields the deterministic continuity equation. Our task to find velocity fields u, x, and t that satisfies the continuity equation. The original flow matching paper proves that if the paths are defined by linear interpolation and the model is trained with the laws above uh, and trained ideally, U theta indeed satisfies the continuity equation. And let's talk about transformers. Transformers possess an excellent property, the handle sequence of arbitrary length. Hence, we can tackle inverse problems where the number of observation varies. The architecture will often embed variables such as time and observations into latent space, solve the flow matching problem there, and output a velocity vector for each parameter. How we can add transformer-based architecture be used to solving Bayesian inverse problems? Given a prepared dataset triples M1, E, and Z, we train the transformers as follows. For every epoch, we sample T from uniform distribution. Then M0 we sample from prior distribution, compute the linear paths between the M1 and M0, predict the velocity vector, and regress it against the true velocity. Model weights are updated using stochastic gradient descent. Here's example with simple nonlinear model. The inference plot shows that the condition on D and E trajectories from any initial uniform sample are nearly straight for well-trained model. Uh, Comparison with existing methods shows that GAN and Y-based approaches do not learn the exact likelihood. And the next problem is the Sayre disease model, describing disease spread in population. S is susceptible, E exposed, E infected, and R removed individuals. And the ODE has control parameters gamma 1, 2, and R, beta 1, 2, and alpha. And we choose the times point at which we measure infected and diseased individuals these times. Our experimental and want to understand the experimental parameters, its time points experimental parameters, and the parameters to be inferred are ODE controls. Here, M. And we can update the posterior distribution of these parameters shown here for observation. Increasing the number of observations reduces the relative error. With 8 observations, it is only approximately 1%. And the next case is recovering a probability field. We solve 2D PDE with few pressure observations at red points at arbitrary coordinates and parameterized boundary conditions E1 and E2. We infer the probability coefficient distribution. Averaging several samples yields a probability field close to ground truth and corresponding PD solution. In this problem as well, adding more observations lowers the relative error. And compared with MCMC, thousands of forward solves are required to reach comparable accuracy. We also compared our method with the classical techniques like genetic algorithms and Bayesian optimization. The table shows that our approach is dramatically faster on CPU inference time, while matching on exceeding their accuracy. And conditional flow matching learns complex nonlinear posterior distributions and adapts rapidly to new tasks that can be posed as standard Bayesian inverse problems. The model accepts a variable number of observations points. The more data, the more accurate the recovered parameters. And we now plan to use the learning parameter distributions for Bayesian optimal experimental design. That's all. Thank you very much for your attention.